Hello everyone, welcome to Brain Blitz Audios. Today in this episode of NEET Preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we're dealing with the chapter Alternating Current. This is the 7th chapter in the grade 12 syllabus for physics in CBSE. So without further ado, let's look at our first question for this episode. The coefficient of mutual inductance when magnetic flux changes by 2 into 10 raised to minus 2 Webers and current changes by 0.01 amperes is option A, 8 Henry, option B, 4 Henry, option C, 3 Henry, option D, 2 Henry. So, how do you solve this question? So, in this question, we're asked to find out mutual inductance when we're given the value of d phi and the value of dt. So we use the formula flux is equal to mutual inductance times current. So change in flux will be equal to mutual inductance times change in current. Which now we can look forward to as m is equal to d phi divided by di. So change in flux divided by change in current. So it's using this formula. Let's plug in the values. d phi is 2 into 10 raised to minus 2 divided by di is 0.01. However, 0.01 is the same as 10 raised to minus 2. So we have essentially 2 into 10 raised to minus 2 divided by 10 raised to minus 2. So therefore, the final answer for mutual inductance, the coefficient of mutual inductance, is 2 Henry. Henry is the unit for the coefficient of inductance. Therefore, the right option is option D, 2 Henry, and we use the formula phi is equal to m times I to find that out. Since we have both d phi and di values given here, so it is easy. You just have to replace phi by d phi and I by di, and then find the mutual inductance. So you got it as 2 Henry. Option D is the right option. Let's look at our second question. In an ideal parallel LC circuit, the capacitor is charged by connecting it to a DC source, which is then disconnected. The current in the circuit, A, becomes 0 instantaneously, B, grows monotonically, C, decays monotonically, D, oscillates instantaneously. So over here, you can see that a capacitor is connected to an inductor in this circuit. There is no potential source. However, it is worth noting that the capacitor initially was fully charged before it was connected to the inductor. So what essentially happens here is a phenomenon known as LC oscillations. So as you can see, the charge gets decreased while the field in the inductor gets increased, and once the inductor's field becomes maximum, the capacitor's charge is 0, and then the inductor's coil will start decreasing, the field will start decreasing, which results in an increase in the charge that is present inside the capacitor. And all the while, current is oscillating from one direction to another. So the right answer is option D, oscillates instantaneously. So the scenario that's given here is the scenario which deals with LC oscillations. And in LC oscillations, V and I are oscillating with respect to time. And this happens instantaneously. Once the instant at which you connect the capacitor to the inductor, then the phenomenon starts occurring. So option D, oscillates instantaneously, is the right option. Let's look at our next question. A capacitor of capacitance 2 microfarad is connected in the tank circuit of an oscillator. Here's the tank circuit. And it is oscillating with a frequency of 1 kilohertz. If the current flowing in the circuit is 2 milliamperes, the voltage across the capacitor will be. We need to find the value of VC. So C has 2 microfarads, so the value of C is 2 into 10 raised to minus 6 farad. The frequency here is given as 10 raised to 3 hertz. And we also have the value of I, which is equal to 2 into 10 raised to minus 3 amperes, because it's 2 milliamperes. So, how do we find voltage across the capacitor? Voltage across the capacitor by using Ohm's law will be VC is equal to I times XC, where XC is the reactance of the capacitor, or the resistance to the flow of current which is produced by the capacitor. That is called as capacitive reactance. So in order to find VC, which is our quantity required, we need to find the value of XC, or the capacitive reactance. And the value for capacitive reactance is equal to 1 by C omega. And omega can be, which is angular speed, can be written as can be written as 2 pi times the frequency. So now we have the capacitance and the frequency. Let's plug in the values. So 1 by 2 into 10 raised to minus 6 into 2 pi into 10 cube. So 2 times 2 is 4. And then 10 raised to minus 6 into 10 raised to minus 3. 10 raised to minus 6 into 10 raised to 3 is 10 raised to minus 3. And so since it is 1 by 10 raised to minus 3, 10 raised to minus 3 goes to the numerator. So now we have the value for XC as 10 cube divided by 4 pi. So this is the value of the capacitive reactance. Let's go on and calculate our potential. The potential VC is equal to I times XC, which is equal to 2 into 10 raised to minus 3 times 10 cubed divided by 4 pi. So that means 10 raised to minus 3 and 10 raised to 3 gets cancelled. 2 goes into 4 2 times, so therefore we have 1 by 2 pi. Let's put in the value of pi as 22 by 7, so it's basically 1 by 2 into 22 divided by 7. It becomes 7 divided by 44. Now let's divide 7 with 44. As you can see, it's not possible, so let's put a 0 and then put a point. So after that, you can add zeros to the right hand side in order to make the number bigger. So we have 70. We can divide 44. We can divide 70 with 44. So put a 1, 44, and when you subtract it, 10 minus 4 is 6. 6 minus 4 is 2, so 26. However, 26 is smaller than 44, so again we add a 0, so that's 260. And if you do 44 times 5, then it becomes 220. And if you do 44 times 6, then it becomes 264. So we'll put 5, 220, balance is 40. And then let's add a 0, so it becomes 400. So 44 times 9 is 396. 44 times 10 is 440. So we'll put a 9, 396, 4, and then that's it. So let's take this much value of the quotient as our answer. So the value of VC is equal to 0.159. Again, using significant figures, again using approximation, we can convert it to 0.16 volts. And that is the answer that we got. If we look at our given options, you see that option A matches with our calculated answer. So therefore, option A, 0.16 volts, is the right option. So over here, the procedure that we did was we first used Ohm's law to get the equation. So VC is equal to I times XC. XC is the reactance. We used the formula for XC, which is 1 by C omega. Omega we expanded to 2 pi into frequency. So we had a term with both the capacitance and the frequency. We put in our values. We got the value for the capacitive reactance. And now we put the value for the capacitive reactance and the current in our equation for the potential. So the potential across a capacitor is now 0.16 volts, which is the same as option A. So option A becomes the right answer. Now let's look at this question. A 50 Hz AC source of 20 volts is connected across R and C as shown in the figure. The voltage across R is 12 volts. We need to find the voltage across C. So the options are 8 volts, 16 volts, 10 volts. Not possible to determine unless values of R and C are given. So the frequency nu is 50 Hz and the total voltage V net is equal to 20 volts. Across this resistance R, we have 12 volts, and we need to find the voltage across C. So this is basically VC that we need to find out. So from reading the question and looking at this figure, we can understand that we have an RC circuit. Now, when we are looking at the diagrams for the potential difference and the current passing through a resistor and a capacitor, if we have current along the x-axis, we notice that VR is in phase with current, while VC lags behind current with a phase difference of pi by 2. So therefore, we'll need to find a value V net, which is the resultant vector of the two potential differences. So let's consider that as V net. So our equation will now be V net the whole square is equal to VR the whole square plus VC the whole square. So 20 square is equal to 12 square plus VC the whole square. Now let's rearrange the equations. We have VC the whole square is equal to 20 square minus 12 square. 20 square is 400, 12 square is 144. Subtract it. 10 minus 4 is 6, 9 minus 4 is 5, 3 minus 1 is 2. So we have VC square equals 256. That means VC is the root of 256. 256 is a perfect square, and it is the square of 16. So VC is equal to 16 volts. So the value of the voltage across the capacitor is option B, 16 volts. And we did that without looking at the values for the resistor or the capacitor. Now, let's look at this question. This is the next question. In an AC circuit, the potential differences across an inductance and resistance joined in series are respectively 16 volts and 20 volts. The total potential difference of the source is. Again, in this question, we need to look at the diagram representing the phase difference between the vectors. So for a vector I along a circuit, the potential difference across the resistor is in phase with the current, but the potential difference across the inductor, VL, has a phase difference of pi by 2 with the current, and it leads the current by a phase difference of pi by 2. So again, we need to find the total potential difference of the source. So the resultant vector is what we need to find, V net. Again, we use the same formula here. V net the whole square is equal to VR the whole square plus VL the whole square. VR is, we have VR as 20, so 20 square, plus VL as 16, which is 16, so we can put it as 16 square. 20 square is 400, 16 square is 256, so therefore the value of V net square is equal to 656. So the value for V net will be equal to the root of 656. Now, 656 is not a perfect square. However, there's an easy way to work around this. We just need to find out the closest values to the closest perfect squares towards which is lying nearby 656. So if we're just looking through our square tables, we will know that 25 square is 625 and 26 square is equal to 676. And 656 lies in the middle, and it is closer to 26 square. Again, the reason why we're following this shortcut method is due to the options given in the question. So since 656 is closer to 26 squared, so we can write the root of 656 as approximately equal to 25.6 volts. So the total potential difference of the source is 25.6 volts, and that is the right answer. All the other options are incorrect because they're either smaller or larger than 656. If we look at 20, for example, 20 square is 400, and that is way far from 656. 31.9 and 53.5 also have the same dilemma, because this is close about 30 and that is close about 54. So therefore, they're way off the mark. The only option that fits this root, or which is close enough to the root, is 25.6, because 26 square 676 is nearby 656, and it is also close by to 625, which is 25 square. So somewhere in between, so 25.6 in the options gives us the right answer, which is option B. Our final question for this episode. With the decrease of current in the primary coil from 2 amperes to 0, value in 0.01 seconds, the EMF generated in the secondary coil is 1000 volts. Find the mutual inductance of the two coils. So, dI in this question is 2 minus 0. dt in this question is 0.01 seconds. The value for EMF is 1000 volts. In this condition, we need to find the mutual inductance of the two coils. How do we solve this question? Again, we use our first formula. In our first question, we use the formula phi, or magnetic flux, is equal to mutual inductance times current. Again, we substitute phi by d phi, the change in flux, and we substitute I, or current, by change in current. In this case, we divide both sides by dt. So therefore, d phi by dt is equal to m times di by dt. Now, d phi by dt in our earlier chapters is equal to minus e. So minus e is equal to m times di by dt. So therefore, the value for EMF can be written as minus m into di by dt. So we have a formula which contains the EMF, the mutual inductance, the change in current, and the change in time. So this is the formula that we're going to be using. Let's write it down again. So EMF is equal to minus m times di divided by dt. Again, minus represents the opposite direction. So let's plug in the values. We have 1000 as the value for the EMF. M can represent the mutual inductance for now. di is 2 minus 0 divided by dt is 0.01. So basically we have 2m divided by 10 raised to minus 2 on the right hand side. On the left hand side we have 1000. On rearranging the equation, we can get mutual inductance as 1000 times 10 raised to minus 2 divided by 2. So this is basically 1000 into 1 by 100 whole divided by 2. So the two zeros get cancelled. We have 10 here. 10 divided by 2 is equal to 5. So the value for mutual inductance is option C, 5.00 Henry. And once again, we found out the mutual inductance by using the same formula. Magnetic flux is equal to mutual inductance times current. And the important thing to note is that this formula, the first one, we can substitute it. We can substitute the values. So flux can become change in flux, provided that current becomes change in current. And then if you can, you could divide by dt on both sides to get the equation E is equal to minus m times di by dt. Of course, we could also straight away say that E is equal to minus m times di by dt. However, the first method that we used is quite easy because you can put this equation easily inside your head. So with that, we got the final answer as option C, 5.00 Henry. And that concludes this webisode on alternating current. If you want to access more of our questions regarding alternating current or other chapters in physics for medical entrance examinations, then don't forget to click the playlist in the description down below. Also, if you would like to support our channel and have access to more of our useful and interesting content such as learn awards, mind maps, NEET preparation, more of NEET preparation or memory hacks, and a lot of other stuff, then don't forget to subscribe to our channel, which is Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.